Hey, it's gonna actually work now. So this first section we introduce kind of some ideas out of calculus by thinking about a couple of types of problems. One problem is by finding something called a tangent line curve at a certain point. We'll talk about what all that means if you're not familiar. And then the other problem talk about is trying to find the velocity. I know it's a physics idea. They're the origin of calculus and the origin of ideas in physics are closely tied together. So sometimes we get a little physics thrown at us. We want to figure out the velocity at a certain instant in time of some object. Before we actually get into that, let me back out of that for a second and let's review a couple other algebra ideas really quickly to make sure it's fresh in our mind. One thing we need to be pretty familiar with finding the slope of a line if we're given 2 points. So let's say we've got point x1, y1, and these are just the coordinates of 2 points on the graph, or 2 points in the plane. So remember, slope we represent with m. That's always bothered me a little bit, so I tried to look into the history on why we ended up with the m for slope, and you don't get really good answers. One kind of origin story I saw, I think, said maybe it comes from maybe German, but doesn't make a lot of sense in English. Anybody remember what the formula is? What do we do? Got the 2 points, and yeah, y2 minus y1 on the top, and then what on the bottom? X2 minus x1. So all that's happening there, yeah, sometimes we memorize the formula without thinking about why that's the formula. All that's happening there is we're saying how far apart are these y coordinates. So if we want to know how far apart two numbers are, we subtract. So we're saying how far apart are the y coordinates, and then we're dividing that by how far apart the x coordinates are. That way we figure out how much the y changes every time the x changes 1 unit. What our slope is. And sometimes call this rise over run. So we're looking at the how much, if we're thinking about a graph, we're thinking about how much it rises left to right, or how much the y coordinates change compared to how much it runs, or how much we change horizontally. Rise over. That's one thing. And then number 2 here. Back from algebra, something else. Probably learned it at the same time you learned slope. You got the equation, the line. Even there's several different ways we can come up with the equation of a line. The main one we will focus on when we're given the slope. I'm going to say a general point on the graph, no specific point, because what else could we do? If we know the slope and we know the y-intercept, that's everybody's favorite. We get y equals mx plus b, or we get the slope-intercept form of a line. But we're not always that lucky. We're not always lucky enough to get y-intercept. Don't know the y-intercept specifically, we can come up with an equation still given any point on the graph. And that one. So let's see, we'll call the slope m, so we can on the same. Our point we'll call x1, y1. Anybody remember what our equation is we use? What our form of the line is in that case? Yeah, okay, so that's looking good. So we got y minus, which one was it? y1, yeah, that's right. We subtract the y coordinate of our point, and that equals something. M, yeah, equals the slope times x minus x1. Good. So this thing, lots of times we call it the point slope. And then if we want to, after we fill in, okay, so the places we plug numbers in, we plug the x coordinate of our point in here, y coordinate of our point in here, slope in right there, and we're going to have a variable y and x still in there. And then if we want to, we can solve it for y, and it will be in y equals mx plus b. Slope in. More typical how we're used to looking at. Oh, that ring a bell? Kind of, at least you remember seeing it before? Maybe? Good deal. No, maybe it's been a while for some of you. Now, we'll kind of have that out of the way. Again, I don't want the algebra to be the reason why we struggle with a calculus idea, because handle viewing the algebra a little bit. So here's, again, these two problems kind of give us some motivation for what we're doing in calculus. So got two problems we're going to explore a little bit in this section. The first one is the tangent problem, or the tangent line problem. So here's our situation. Get some definitions. When we talk about a tangent line, the term tangent comes from the Latin word, means touching. So we have some line that touches a curve in the plane. We're thinking about with a tangent line. Here's a picture maybe. So here our curve's a circle. It doesn't have to be. Curve in the plane, circle, and we would say this, I guess that's pink line there touches the circle. Say that line is tangent to the circle, or that is a tangent line, circle. The idea here with this definition is that we have a line that touches the circle or touches our curve only one time. It only touches it. We have a curve that's maybe more wavy. It's not just a simple circle. It has some kind of wavy polynomial looking graph, then definition is not going to be quite good enough for us to talk about what we mean by tangent line. So let's look at another picture. here. We have here the black one be our curve. And if we just say tangent line only touches our curve one time, and blue line here looks like maybe that would be a tangent line. That's not really what we want. We want our tangent line to kind of go the same direction as our curve is going at that particular point. I like that blue idea there. And for sure, the pink line touches our graph at point P there, but what's the issue with our proposed idea that it just touches the graph one time, touches our curve one time? Pink one, why is that messed up by the pink line? Yeah, because it also touches over here. That's not quite enough of a definition, because the pink one looks more like what we're after. The blue one doesn't. So we need to firm up that definition a little bit. So think about this problem. We want to find an equation tangent line to point 1, 1. We're going to call it point P. So we know a point that it has to go through. So the other piece of information we would need to come up with the equation for that line is the slope. That's going to be our challenge. It's going to be our challenge, coming up with the slope of a particular tangent line. I don't remember if I have a slide in here, but we have one other term we need to talk about. So we've got our tangent line. So if we're going back to thinking about a circle, tangent line, then that would be it touches the circle at one. There's another special kind of line that we're going to use. Here has a special name. Boy, that was ugly. We have one that touches at 2 points. This one we just spent a little bit talking about with that tangent. In this case, where we're touching 2 places, you may know that one. It starts with the S. I gave that away. Secant, yeah. Secant or secant. So let's look at why finding this slope gives us trouble. Trying to find, well, great. Trying to find slope of the tangent line. The graph y equals x squared, 0.11. Okay, we know how to find slope. Once we find slope, we can plug that into our point slope form and the equation of the problem that we only know 1 point on our tangent line. When you've seen stuff like this in algebra class before, you may have like a straight line equation, or maybe you figure out another point some way. We don't have that luxury. So let's see. I've got the graph here. Let's see how this works. Okay, so 4. Cool. All right, so let me ask you a question as far as looking at this. Okay, so there's that version of this graph, or we could switch it that way. Which one's easier to look at, white or black? This one, you think this one's better? there's our situation. We've got, this is the graph of y equals x squared when parabola affected that, and we want to know the graph of the tangent line, this curve at the point P, and we said that point P was 1, 1. So the idea is we want a straight line that only touches that curve right at that one point. That's what we're going with right now. We'll get a little bit better definition shortly. So the issue, the problem we have is we only know that one point, the point 1, on our tangent line. Okay, we can figure out as many points as we want on the parabola. Having more points on the parabola doesn't solve our problem right away because we don't care about the other points on the parabola so much as we care about other points that will be on the tangent line. So what can we do? Where we actually finally get into the calculus idea. Yes, you're getting there. Okay. So one other thing to think about is another way that we're having a problem. If we go back to how we calculated slope, we can't do it with just one point because, say we made both of these 1, 1. On top, we'll get 0. That's not a problem. But on the bottom, the issue there, if both of these x coordinates are the same, we can't even get an answer out of this. Because if x2 and x1 are the same, what happens to our slope? What would we call that? If these are the same, then the denominator will be 0. Yeah, so our slope will be undefined. So one strategy we can take is we can just pick some other point on our graph here. There we go. We can pick some other point on our graph. So I'm just going to pick this point, call it Q. Right now it's down here, maybe a little hard to see. I'm going to start it at 0, 0. So if we find slope between P and Q now, since they're not at the same point, we can calculate. Then we could take that slope and our 0.11, our P point, plug that into the point slope form of a line, and we could get a line, but it's not going to be a tangent line. Is it going to be? It's going to be secant line. Cutting through, okay, secant comes from Latin that means to cut. So it's going to cut through our graph. We want the tangent line that only touches at P. So let's look at something that happens here. So we're trying to estimate tangent line, the one that only touches right at P. We could get a better estimate, right? Like we could make our, I guess we call this orange, and we could make our orange line be closer to what our tangent line at P would be. Anybody see how we could do that? P's fixed, but what could we do? That's a good idea. But in this situation, we want to leave, that's a good idea, but we want to leave P fixed right now. So leaving P fixed where it's at, 1, 1. How, think about your idea then. We could just move Q, and if we get Q closer to P, let's look, make sure we're right, but if we move Q closer to P, I got a little slider down here. If we move Q closer to P, And our slope's getting, our slope of our secant line is getting closer and closer and closer to what we would expect out of our tangent line. So if we get our 2 points really close together there, we're getting a better and better estimate for what the slope will be when it only goes through P. And take a look at this spot right here. And I've got this set up where when my points move around, it gives us the slope of our secant line. So let me back it off a little bit again and then watch that. When Q is over here somewhere, so right now, I know that's kind of small. Right now the slope's like 1.28. Slope of our secant line. And then as I move Q closer to P, anywhere like 1.5 there, 1.71, 176, there's 1.9, 1.96, 1.98, 1.99. So when the x coordinate of our Q point, 0.99, slope between Q and P is 1.99. If we have a problem, you could say, why don't you just move it to 1? And if we make A1, then we already know what happens. We've seen it, right? Our slope formula breaks down as undefined when P and Q are both at the. So here's the idea. We're smart. Might not feel like it sometimes. Okay, we're smart. We can kind of figure out what our slope's supposed to be, even though we can't just calculate it with a slope formula. Did you kind of see where we were headed? Where we were headed when let me back up for point Q again a little bit. So looking at the little box, that's a slope of 1.52, 1.71, let's see, 0.88, 0.94. If we get a little closer, 1.97. We'll get a little closer, 1.99. Anybody got a feeling about what the slope should be when it's right at P? You tell what we're getting close to? 2. So even though our formula gives us undefined when we're exactly there, we can pick out the pattern and we can tell that our slope's supposed to be 2. Same thing works if we go on the other side. Let me move Q over on the right side of P. So now, watching our slope calculator there is 2.22. I move a little bit to the left, 2.19, 2.14, 2.09, 2.05, 3, getting really close together, 2.0. So see the pattern, how when we get our points closer and closer together, we have an idea of where we're headed, even though we can't actually get there. And like we're getting super close to 2, but right when we think we're going to get to 2, everything messes up and it's undefined. We come from the other side, it's a little bit bigger than 2, but it's getting smaller, getting closer and closer to 2, but right when we think we're going to actually get 2, it's. So this idea of being able to tell, and being able to figure out that as we get closer and closer to having our 2 points together, we're watching that slope, the closer our points get together, the closer our slope gets to 2, even though we can't actually get our slope to exactly equal to with 2 points. That's a calculus idea. That's called a limit. Some of you have heard of it before if you've had calculus ideas in the past. That's what we call a limit. So that's what we're after. Let's back at our slides here. So same idea here in the slide, but it's just not animated. We can, any Q and P we pick, as long as they're not the same point, then we can figure out the slope. Then We check the values. Come in from, this is the bigger side, so this is like coming in from the right side. Get close to 2 for our slope. And these are smaller values, smaller than our x-coordinate of 1. So as we come in from the left side, our pattern shows us we're getting close to 2. So we can say this. And we've got some, we can tell slope of the tangent line should be right at 2. And the way we say that, we say that the limit of these slopes as our 2 points get closer and closer together, so this says as Q gets closer and closer to P, okay, that's got to be our slope of our tangent line, which we figured out as our Q points x-coordinate gets closer to 1, that's the x-coordinate of P, and our slope, 2. So this says the limit as our x-coordinate approaches 1, 2. And this thing's just the slope, squared minus 1. So we can figure that out. And if we take that slope of 2, our 0.11, we get the tangent line. It's the tangent line. So we plug it in point slope form, solve it for y, we get y equals mx plus b, slope intercept form, we get 2x minus 1, and we can check it since we've got our graph out. I'm gonna turn that off, and then we said it should be y equals 2x minus, should be our tangent line. Let me change the color here, so different color maybe. Maybe I don't know how to do that in touchscreen. Hang on, let me get Q out of the way here. There's our point P. There's our tangent line. 2x minus 1. It only touches our graph, y equals x squared. 1 point. Right at the point 1. What we're after, that's our tangent line. Okay. Kind of hanging in there. The main idea right now is that as our points get closer together, we can tell that our slope's supposed to go to 2. Even though we can't actually calculate that, we can tell by getting points closer and closer together. Limit idea, what we're really after. And the rest of the stuff, as long as you just kind of have a big picture, other stuff. All right, so that's our tangent line problem. How do we figure out the equation of a tangent line? We can take a secant line and slide our points closer and closer together, figure out where our slope's headed when we do that, and we can come up with the slope of the tangent line. There's our non-animated idea. We got it. And that's one problem. The other problem, so we came at it from a geometry perspective, talking about the slope of a tangent line. So in this problem, we're kind of approaching things from a physics angle. So anybody ever heard of Isaac Newton? What do you know about him? What's the famous one? If you only know one thing, what's the famous one thing? Yeah, well, gravity. Yeah, that's good. And then what story goes along with that? That's what apple falling on his head, right? That's Isaac Newton's credited as one of the developers of calculus. So that's where we get all this physics stuff in there, because that was kind of his driving force behind coming up with some of these ideas, was deal with physics problems. Leibniz was kind of the debate is if one copied the other, or if they co-discovered, or all that history. Let's think of this problem. Okay. It says, suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. We want to find the velocity of the ball after 5 seconds. So velocity, I don't know how much physics any of you have had. Velocity, we're thinking not just speed, we're thinking speed and direction. So here, since we're moving up and down, we would say positive would be up, negative would be down, the y-axis. So we want the sign and the magnitude, the number. Okay. So we don't have to come up with all the equations and stuff on our own. Okay, we've got a little bit given to us here, thanks to Galileo. He's got the free falling body. We're like we do in math class. Okay, we're pretending like stuff's not really like it is. We're gonna say we're not thinking about air resistance. We did our experiment in a vacuum. If that's the case, then we've got an equation, the function s of t. S in physics usually used to represent what we call a position function, where something located at a certain point in time. T's time in seconds. And it says if the distance fallen after t seconds is denoted by s of t and measured in meters, then Galileo's law is this equation, s of t 4.9 times t squared. Problem we're into, okay, so velocity, we want to know how fast something's going. And we can even just think about speed right now. If you want to know how fast something's going, what information do you need to figure that out? Distance and time, that's right. So we need to know how much distance is covered over how much time. Where we come up with speed and then specifically velocity. So problem is we want to know how fast this ball is going exactly at the point in time after 5 seconds have passed. So we don't have like a time interval where we can just say, okay, it went this far after this amount of time. We want to know how fast it's going at this one exact instant in time. So it's a little trickier. We don't have an interval here. So we can figure out the average velocity, not at an instant, but we can figure out the average if we do give ourselves a time interval. So we want to know the velocity right at 5 seconds. But we can get an estimate if we go out just a little bit in time. So maybe we go out a 1/10 of a second. So we figure out where our ball's at 5 seconds, where our ball's at 5.1 seconds. Track those distances or those positions, figure out how far it's gone. And 5 minus 5.1, that tells us time interval. We're down to a 1/10 of a second. If we do that, then we can figure out the average between 5 and 5.1 seconds, the average velocity it's going in that time frame is 49.49 meters per second. That's not what we want. That's just an estimate. We want the exact value right at t. Not between two t's, but right at t. what can we do? I'll post these slides if you want me to. We can take kind of the same approach we did with the points P and Q. So on the last one, we wanted slope of the tangent line. What we did is we figured out the slope of the secant line and then let our points on the secant line get closer and closer and closer together and found the pattern. Here we can do the same thing with our time intervals. So here we're figuring out our average velocity over the time between 5 seconds and 6 seconds. Or we can do between 5 and 5.1, between 5 and 5.05. We can get as close to 5 as we want to, and then we can observe the pattern that's happening with our average velocity. You just had to guess based on those, starting from top to bottom, trying to tell where our average velocities are headed. What would you say? Looks like 49, right? By the time I get to the second row, it's 49 point something, and the point something part is just getting smaller and smaller. And you could suppose that if we made another row, and it'd be 49 point something even smaller. So at time t equals 5, what do you think our velocity is going to be? So as our time intervals get smaller and smaller, it looks like we're getting to 49. So say through this limiting idea that at time t equals 5, our not average velocity anymore, what we're talking about then is instantaneous velocity, right? At an exact point in time, t equals 5 would be 49 meters per second. And I guess here I said I gave you the signs backward before. I guess since we're thinking about we're traveling down, then they're calling down positive 49 meters. So two pretty different problems. But we can take a really similar approach coming up with a solution. And in fact, you can even phrase this problem just like we did the tangent line problem. You can think about it geometrically too, sorry. What we would do, I thought I had a picture of that graph. What we would do is we could take our equation for the velocity, (4.9t squared), make the graph, and since we're in t's, our horizontal axis would be in t, our y-axis would be in s, be in position. Okay. And what we could do is we could figure out our average velocity, which turns out to be slope between 2 points, and get our t, our time intervals, closer and closer and closer together. So think about this, this little, if our average velocity, let me give us a visual here. Wrong graph, same idea. If our average velocity, let me get our picture back. Maybe. Sorry. And the touch screen are not getting along today. Our average velocity is the secant line, because all the average velocity is how far do you, or how far does our graph go up? How much is our position change? Divided by how much time has passed, average velocity, also known as the slope of the graph. Then what's going to be same idea as the slope of the tangent line. If average velocity is the slope of the secant line, the slope of the tangent line is going to be instant velocity. Instantaneous. So really the same idea. So let's look at types of problems we have in this section. We didn't focus on doing particular calculations. This section is more conceptual. And so let's look at what kind of stuff we've got to with. Maybe we'll do a couple together. So the first couple of problems they're just should be easy little reviewing. First one says find the slope of the line between 2 points. Slope formula on 1 and 2. Sorry, that kept scrolling. I promise I know how to use it. It just looks like I don't today. So the first couple, just find the slope, no big deal. Just to get you warmed up and in gear, we've got find the equation of the line passing through the given points. So use the 2 points to find the slope. Use one of the points in the slope in the point-slope form. Solve it for y, you get the equation. And number 4, we should be warmed up. So here's more along the lines of what we did. So red numbers are the change person to person. Got a tank. Mine says it holds 1,000 gallons of water, drains from the bottom of the tank in half an hour. Values in the table show the volume of water that's still in the tank after t minutes. After so many minutes, how much water is left in the tank. Part A here says if P is the point 15,250, so in 15 minutes we got 250 gallons left in the tank. Find the slopes of the secant lines, PQ, when Q, point on the graph with the following value. So it's given us a fixed point P, just like we did, except instead of 1, 1, fixed point P is 15,250. And then we just want to find the slope between that point, 15,250, and these other points it's given us is Q. And so really we just have 5 times to use the slope equation, slope formula. Does that make sense? So the first time we're just using this point and this point to find the slope. And we use this point and this point to find the slope. Fill those in. It's the same thing I did with my little slider, except 5. And part B is just asking us to find the pattern. Really, it says estimate the slope of the tangent line. But this time it's saying by averaging the slopes of 2 adjacent secant lines. So it's taking the average instead of necessarily looking for the limit. So since we're concerned with the point 15,250, this one, the 2 secant slopes that you want to average together, okay, you either want to average together, ones that are close to 15. So you can do 20 and 10 maybe. So average, you just add together and divide by 2. Nothing fancy. Okay. 5 is similar, it's just not word problem form. It gives us a point P that's on the curve, and it gives us the equation for the curve. It's 3 over 4 minus x. It says if Q is the point x, comma 3 over 4 minus x. Figure out the slope of the secant line. So again, we're taking the point 5, negative 3, and for our x coordinate on Q, it'll be 4.9 on this first one. And then to figure out what the y coordinate is, you plug it into 3 over 4 minus x. Is the slope. Add there, and then it'll ask you the same thing on part B. It'll say, guess, what would be the slope of the tangent line then? This one, it doesn't tell you to take the average. It just says, use the limit idea, take your guess. In C, we use the slope that we guessed on part B and the point slope form. Yep. Yes, we will. I just want to show them to you, and then we'll pick one if you want to. We'll be glad to do one. And 6, I think I've only got, we're going here, 7. I only got 7. Yeah, no, there's several steps on each one. You're not going to have like 50 or okay. This one's really similar to the one with the dropping the ball. This time we're throwing it in the air. Gives you the equation there. Seven gives us a table. So let's see, which one seems most confusing? Which one you want to do together? 4 or 6? Which one? 4 or 5 or 6? I guess. 5, yeah. If we need to do another one, we will. Okay. Let's look at this one. Again, your numbers would be different, but it would be the same process. So we've got a point P that's 5, negative 3. Let me paper here. Okay. And our curve is y equals 3 over 4 minus x. And what we're going to do, we're going to be dealing with points that are Q's. They're going to be in this form. Because to figure out our y value, we just plug in for x and solve for y. So how are these labeled? 1, 2, okay, Roman numerals. So first one, 1, little I, we've got 4.9. So that's just our x value of our Q point. Here to figure out our Q point, x value is 4.9. And then we're going to plug in x at 4 minus 4. Figure out first part, we don't have a calculation, it's 4.9. And break out a calculator. So let's see, 3 over 4 minus 4.9. And then did it tell us how many decimal places? 6 decimal places, so we're being pretty precise here. 6 decimal places, so yeah, I get negative 3.33. That's our point we're using. So now we want the slope of between this point that's the way they write it is MPQ. That's what this PQ means. It means the slope of the line between the point P and the point Q. Given this Q. Now we're just using the slope form. It doesn't matter which point you call which. So slope of MPQ in this case one of the y values. We just got to make sure we put the same point in the first spot both times. So let's see, we'll do, I'll do the p y value first. So -3 minus -3.333333 over, we'll put our p coordinate first, 5 minus 4.9. That makes sense where I'm getting all those? So let's see. -3, that turns into plus 3.333333, and divided by 5 minus 4.9. What'd you get? Or, oh, it's up to me. So I get 3.3333. What my calculator gave me. Let's see if WebAssign likes that. I do the same thing with 4.99. A little bit of a drag, but copying most of what we did already. Q, kind of figure out what it's going to be, and it's going to be 4.99. This time, instead of plugging 4.9 into our equation, we'll plug in 4.99. 3 divided by, and I'm doing a parenthesis there if you're doing it in a calculator way, 4 minus 4.99. Here our y value of our q. Yep. Check me too if you're working it. Let me know if you get something different. And same song and dance. It gets a little -3 minus 3.0303 over 5 minus 4.99. Here I get 3. This one's kind of boring. 3.0303. Just keep going. It's not. Well, we got one more that direction, and then it goes the other direction. Now we got 2 more. Do it again with 1 more 9. Do it again with 2 more 9s. And the other way is just values that are a little bit bigger. I already have a guess personally on where we're headed for the slope. What does it look like? So we take this one, it goes down a little bit. I'm betting the next one goes down some more. What does it look like we're headed toward? 3 probably. Kind of, you'll have an idea if you punch in the next in the calculator and you get 7 for your slope. You can go back and double check. Probably wrong key. Okay. So then my guess would be 3. And then using that slope, we want to find an equation of the tangent line. So we can do that part too, to have 1 more of those. So I'm guessing the slope is 3. Even though I didn't fill out much of my table. Then my point, 3, 5. Grant that was it. Oh, 583, sorry. So plugging into point slope, like y minus, be careful on these if it's been a while since you've done them especially, got to be minus negative 3 times x. And we can solve that for y. Subtract 3 from both sides. Should be it. That one's a little labor intensive, but it's not take you a minute. Questions on that one? I do kind of tend to think that's the most confusing looking one. If you run into other ones that give you trouble, just let me know when we, on Wednesday. We'll work whatever we need to work, whatever part or whole thing, whatever. Okay. All right, yeah. So it's Friday, so I told you get kind of ripped off having to meet 4.5 hours for a 4-hour class. So I try to let you out early on Friday as much as I can. Okay, so, if anybody came in after I called attendance, I don't remember if you did, but just let me know so I make sure I get you here. Upload the slides. Yes, sir. Yes, I will.